I'm going to talk about my attempt to understand intelligence. So as a disclaimer, this talk contains my personal opinions besides academic accepted facts. So my purpose is to understand intelligence. But why? To build a superior intelligence than what currently we have. And why? Because to answer my questions, and the purpose of this talk is to raise the correct questions in your mind about intelligence. And why should you care even? Have you ever thought, what are we doing in this strange universe, like a dust wandering among 100 billion galaxies? And have you ever sit in a corner thinking how strange it is to be self-conscious? If you had these questions, then you might like this talk. Well, apart from you and I, someone else had this question too. Maybe that's why we are here. And I call that person the universe. Well, the universe was far ahead than us, and it came up with a plan. It started with everything that he had, with a combination of all the molecules, including carbon, to build more sophisticated, more complicated structures that we call it proteins. But it didn't start playing. It started playing with that and came up with more sophisticated structures with codes, which we call it DNA. And the resulted entity came up with a very interesting property, self-replication. And we call it life. Again, universe didn't stop playing. It started with changing these codes gradually through the time. It had a lot of time. And with a very brutal way, survival of the fittest, it came up with something we call it evolution. And the universe was really lucky because it ended up with the most interesting and most amazing entity in this world, which we call it intelligence. Well, but what is intelligence? Similar to other higher level concepts, abstract concepts, it's really hard to define what intelligence is. Well, simply we can attach it to humans because we are intelligent creatures, right? But before that, I invite you to watch this video with me. Oh.
And finally from us here on the webcast today, a story that might cause some of you to question whether or not we human beings really are the smartest creatures here on planet Earth. Japanese researchers created an intelligence test that pitted humans against chimps. And in the end, we look like chumps. Here's Bill Blakemore.
First test. Can chimpanzees count from 1 to 9 in the right order in return for a peanut or other tasty reward? Yes, they can. Now, if you just flash the 9 numerals for a moment, then cover them, can a chimpanzee remember where each numeral was and still get the order they were in right? Yes, for another tasty treat. This chimp got this wrong once, but thought nothing of it and, undaunted, went right back to getting them all correct. Now, if you flash just some of the 9 numerals, then cover them, can a chimp, A, remember where each was, and B, in the right order, even though some were missing? Yes. Slowing down, not one bit. And note, chimps can also eat and memorize at the same time. Not only that, if right after the numerals are flashed, the chimpanzee is then distracted, say by some monkey business over to the right off camera, or perhaps by another good-looking chimpanzee, and then returns to it, no problem. Just keep the goodies coming. Now, can another primate species, the adult Homo sapien, do the same? Well, okay. And again? 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 One more try? Well, okay. But actually, chimpanzees did much better than humans in this flash and remember test, leaving the Japanese human researchers scratching their heads. One possible theory: chimpanzees care more than humans about peanuts. Bill Blakemore, ABC News.
Well, quite fascinating, huh? Let me see what did I do. Well, it is really hard to define intelligence. There are many different definitions, but since this is my talk, I'm going to give my own definitions. I define it as the capacity of the imagination or the simulation of the world or the environment and predicting based on these simulations. Basically anything that can compress the information around it and predict the future based on that, then it's an intelligent entity. Well, problem solving also maybe fall in this criteria. But let's wait a bit. If this is the definition of intelligence, can we build intelligence based on that? Well, I think there are two ways of doing this. First one is understanding how our brain works. I mean, studying it biologically. And the second one is understanding how it functionally works by understanding symptoms, what it makes us able to do. The first attempt doesn't really look interesting for me, but actually there has been a lot of attempts and research going in this part. But since there are almost same amount of neurons as we have in our universe in terms of galaxies, it is really hard to come up with a proper model of our brain. So I think we need another intelligence to solve our brain, then we can solve intelligence. So it's kind of no way for me. So having said that, let's try to look at the history of the attempts that humans tried to solve intelligence. It started from 1950s officially, and humans started thinking seriously about building an artificial brain. Pitts and McCulloch were the first one to adopt artificial neurons, and Alan Turing introduced his famous test, which is not relevant anymore. And at 1950s, at Dartmouth conference, artificial intelligence term was coined. And after that, at 1965, Ivanchenko introduced a multi-layer neural network, which was the earliest version of deep learning. And I'm going to come back to this, why it was not a hype at that time, but it's hype right now. And at 1970s, Marvin Minsky told us that in 3 to 8 years, we will come up with a human-level intelligence. But it didn't happen. And 1975, Verbos introduced backpropagation, which was the core functionality of whatever we have in machine learning today to train our models. But then there was no big progress in this field, and investors and researchers lost their interest. And it was beginning of a long, long winter. Well, what was the reason that we had this winter? Because most of the models was inspired based on the brain, and it was working inefficiently. We didn't have enough computation power. We didn't have enough data. And above all, we didn't know why by adding more layers to neural networks, it doesn't increase the capacity of it. Why it doesn't make it better. Because Ivanchenko already introduced a multi-layer perceptron, deep learning, but it was not working by adding more layers, and we didn't know why. But was there a Jon Snow to save us? Yeah, of course we had, but his name was Seppo Kryter. How many people know this guy? Here. One? Okay. Interesting. Well, Seppo Kryter did a very simple thing, but revolutionary. He understood, he discovered why we are not able to train a deep learning model, why by adding more layers to a neural network we cannot increase its capacity. And basically it lies in this photo. As you can see, this is a multi-layer perceptron. It has a last layer, which we calculate, if you know a bit of machine learning, which we calculate error function at the latest layer, and then we try to backpropagate the error through the layers to the earliest layers. But the problem that we didn't know was, when we calculate the error and try to backpropagate it to earlier layers, it vanishes to 0 or explodes to infinity. That's why we were not able to train the earlier layers, and we were only training the latest ones. And this problem was called vanishing gradient problem, and Sepp Hochreiter discovered it. And by discovering it, we came up with tricks and engineering ways to eliminate this barrier. And that was deep learning, to allow us to train a multi-layer perceptron with a lot of layers. Well, if you look at the history of artificial intelligence, it started from 1950s with a very higher level perspective by looking at reasoning, intuition at the same time, and trying to build even general purpose problem solvers at those times. But then, since we were not really successful in that, we started by delving into that in more application-specific terms. And we came up with machine learning techniques to apply it in specific applications. And then, from 2000s, we started with a deep learning excitement. And at 1997, Jürgen Schmidhuber, who was the advisor of Sepp Hochreiter, proposed long short-term memories, LSTMs, which all of us are using that in our phones when we do speech recognition, when you are using Siri, and a lot more. At 1998, Yann LeCun, Facebook AI director, proposed convolutional nets, which was the first success in document recognition, and now it is used widely in many, many applications. At 2006, Jeffrey Hinton, Google's AI director, found a way to train in an unsupervised multi-layer neural network using deep Boltzmann machines. And at 2009, Saracen used the first NVIDIA GPU to calculate massively big parameters of a model as a neural network. 2014, Jan Goodfellow introduced generative adversarial networks, which I'm going to talk about it a bit more because it's really interesting. And at 2016, DeepMind of Google introduced AlphaGo, which beats the first champion of Go, and that was revolutionary. But DeepMind said we need to go a bit more deep. And one of the examples that I'm going to show what DeepMind did is in this video. This is quite interesting. It's about Breakout Atari game. The model doesn't know anything about what a ball is, what a racket is, and anything else. There is no prior information. The only thing given to the model is that it needs to maximize the score. So in the beginning, it's playing like a dumb human. After 2 hours of training, it becomes like a human expert, doesn't let the ball go, and tries to accumulate the score. But the magic happens if you train a bit more. After 240 minutes of training, the magic happens, and it finds the way to maximize the error with the less effort by carving a tunnel in the corner and let it go from there. So this is quite interesting. And one of the other things that I mentioned was generative adversarial networks. It looks like kind of imagination, because when it was first introduced, it was about generating samples out of our training set. It contains two parts. One is discriminator, and the other is generator. This is the discriminator, and that is the generator. And we have a training set. So what does it do? It first tries with random noise. The generator spits out a random image, for example. And then the discriminator compares this image with the real ones and penalize it. And each time, generator becomes better and better at generating a real data, real sample. And if you train it more, then the generator will be able to even spit real images for you, and that's called generative adversarial network. This is how it works. And this is kind of maybe an imagination of neural networks that we think. Well, I'm not going to go into details of this, but this is quite interesting, but there is something lacking in there, and it's not all the picture. What we had so far is called VKI. It's very application specific. It doesn't transfer from one domain to the other, and it's not even close to human level intelligence. If we go back to the chimps and try to explain that, because we don't want to let the chimps win the game, of course, there is a hypothesis called cognitive tradeoff hypothesis. And that tries to explain why chimps are better than human in short-term memory. There is a model called triune brain, and it classifies the brain into 3 different parts. The third one is the most vital one, reptilian brain. It's responsible for fight or flight, aggressive drives, vital behaviors, blood pressure, pumping the heart. But the second one is mammalian brain, which generates emotions, center for habit and memory, which we have in chimps, and is better than humans in this part. But the first part, which is developed in sapiens and primates, it's the rational and logical thinking part. And it allows us to do abstract thinking and do imagination. And one of the hypotheses are that the consciousness belongs to this part of the brain. So if you look at this photo of this woman, in every photo, you don't really need to think about what is she feeling. The feeling you get from the photo is immediate. You don't need to think about it, right? But what about this one? If you sum 1 plus 2 plus 3 till infinity, what's the reason? What's the outcome? You are expecting it to be infinity, right? But it's not. It's minus 1 over 12. Yeah, that's mind-blowing, but it is what it is. But you cannot really intuitionally say, yeah, it's minus 1 over 12. Everybody knows. No, it's not like that. It's not as easy. You need to prove it. So there are 2 different ways of thinking. 2 different ways of thinking. We call it dual process theory. If you have 2 systems, system 1 and system 2. It's a bad naming, right? System 1 and system 2. System 1 is intuitive. System 1 is fast. It's exactly what you do when you recognize your friend, what you do as, like, recognize your parents when you're a baby. Face recognition is something intuitive. It's really fast. Nobody teaches you to recognize your parents. Nobody teaches you how to do face recognition. But the system 2 is analytic and is slow, and it needs careful analysis, it needs energy to do so. And if you want to, for example, learn to ride a bike, you need to try hard, you need to practice. If you want to prove a mathematical theorem, then you need to do some effort. And this is system 2, which is reasoning. But I think we are missing a powerful link between system 1 and system 2 in artificial intelligence. And this is what I came up with, what I call it knowledge framework. If you look at the core of it, it's basic understanding of our environment, system 1. It is intuitional. Whatever we see and whatever we do automatically, like a pattern recognition. But there is a layer above it, which is our reasoning, which we do like mathematicians do, prove theorems or any other reasoning. But when you observe your world, then you can understand the laws governing the universe. And that is one level more, which I call it physics, modeling the environment. But you can even go more deeper by eliminating the constraints or the laws governing our universe. Then you can build even a better, a more general framework, which we call it mathematics. There is no constraints there. You can build any world in there. But I think we can go even one more step deeper, which is our imagination. In mathematics, everything is symbolized. And those symbols are the barriers to communicate the knowledge. That's why we write a book, just to transfer a very simple thing that we can come up with in our imagination. So maybe we need to go a little bit step back to the imagination and build our mathematical framework or symbols based on that to be able to communicate this better. Because after all the things that we know is subjective. But what else are we missing? I think we are missing consciousness, computation power, and curiosity. About consciousness, I think an intelligent being doesn't necessarily need to be self-conscious. It was only a tool for evolution to preserve what it had, to bring something up, like humans, to bring ourselves to this point. Consciousness was only the motivation engine of the universe to do this. Computation power. We use a lot of CPUs or GPUs just to train very, very simple models, but our brain only uses 13 watts. Why should we really stick to silicon? Because I think biological organs are doing far better. Maybe there's an answer in that. And about the curiosity, I'm going to invite you also watch this video with me.
There are many research projects about teaching an AI to play video games well. We have seen some amazing results from DeepMind's DeepQ learning algorithm that performed on a superhuman level on many games, but faltered on others. What really made the difference is the sparsity of rewards and the lack of longer-term planning. What this means is that the more often we see the score change on our screen, the faster we know how well we are doing and change our strategy if needed. For instance, if we make a mistake in Atari Breakout, we lose a life almost immediately. But in a strategy game, a bad decision may come back to haunt us up to an hour after committing it. So, what can we do to build an AI that can deal with these cases? So far, we have talked about extrinsic rewards that come from the environment. For instance, our score in a video game, and most existing AIs are, for all intents and purposes, extrinsic score maximizing machines. And this work is about introducing an intrinsic reward by endowing an AI with one of the most human-like attributes, curiosity. But hold on right there, how can a machine possibly become curious? Well, curiosity is defined by whatever mathematical definition we attach to it. In this work, curiosity is defined as the AI's ability to predict the results of its own actions. This is big, because it gives the AI tools to preemptively start learning skills that don't seem useful now, but might be useful in the future. In short, this AI is driven to explore, even if it hasn't been told how well it is doing. It will naturally start exploring levels in Super Mario, even without seeing the score. And now comes the great part. This curiosity really teaches the AI to learn new skills, and when we drop it into a new, previously unseen level, it will perform much better than a non-curious one. When playing Doom, the legendary first-person shooter game, it will also start exploring the level and is able to rapidly solve hard exploration tasks. The comparisons reveal that an AI infused with curiosity performs.
So, that's really interesting. How we can introduce curiosity in our system. But what should we do now? My conclusion is that we are missing a link between intuition and reasoning. We don't necessarily need to build consciousness, and we don't necessarily need to build it on silicon. And we don't necessarily need to copy the brain, because it doesn't guarantee that it's the best design for intelligence. And if we want to build a superior intelligence, I think we need to build an agent with the ability of evolving, defining a world which has different levels of complex rules governing it, and rewarding the agent based on predicting the world better. And change the agent continuously to optimize the imagination capacity. Then we will reach something that we want to have. We are the eyes of the universe to percept itself. And of course, I cannot let this talk finish without a quote from Jürgen Schmidhuber.
A new type of life is going to make the universe intelligent. Now, of course, we are not going to remain the crown of creation. Of course not. But there is still beauty in seeing yourself as part of a grander process that leads the cosmos from low complexity towards higher complexity. It's a privilege to live at a time where we can witness the beginnings of that, and where we can contribute something to that.
Thank you.
Thank you, Amin, for your talk. Unfortunately, we ran out of time for questions, so if you have any questions, please try to find him at the bowl so you can ask your questions.
The purpose was to make questions, not to ask the questions.